Have you ever looked up at the night sky and wondered, how did all this begin? It's a question that has captivated humanity for millennia. We see a vast expanse of stars, galaxies, and cosmic wonders. Where did it all come from? The quest to understand our universe's origin is one of the most fundamental scientific endeavors. We peer into the depths of space, using powerful telescopes as our time machines. We study the faint afterglow of the Big Bang, the event that birthed our universe. Join me as we explore this epic journey. Epic. Before we dive into the details of the Big Bang, let's take a moment to appreciate the sheer scale and grandeur of our universe. Our home galaxy, the Milky Way, is a swirling disk of hundreds of billions of stars. And it's just one of trillions of galaxies scattered throughout the observable universe. Each of those galaxies is a vast island of stars, gas, and dust. They come in a variety of shapes and sizes, from majestic spirals to elliptical behemoths. The distances involved are staggering. The light from distant galaxies has traveled for billions of years to reach our telescopes. It's a cosmic time machine, allowing us to glimpse into the universe's history. The quest to understand the universe's origin is a search for a grand narrative. It's an attempt to answer some of the most profound questions we can ask. Where did we come from? How did it all begin? What is our place in the cosmos? Scientists have pieced together a remarkable story, a cosmic epic that spans billions of years. It's a story of incredible density and heat, of rapid expansion and cooling, of the formation of the first atoms and the birth of stars. In the following sections, we'll explore this grand narrative in more detail. The Big Bang Theory is the prevailing model for the birth of our universe. It suggests that the universe began from an extremely hot, dense state about 13.8 billion years ago. Think of it as an explosion, but not like a bomb going off in space. Instead, imagine space itself expanding rapidly from a single point. Space itself expanded, carrying galaxies along for the ride. The early universe was incredibly hot and dense. The Big Bang Theory is supported by a wealth of evidence, including the observed expansion of the universe, the cosmic microwave background radiation, and the abundance of light elements. To truly grasp the Big Bang, we need to take a journey back in time. Imagine rewinding the universe's expansion, like a film running in reverse. Galaxies draw closer, and the universe becomes denser and hotter. As we go further back, we reach a point where stars and galaxies dissolve into a sea of elementary particles. Protons and neutrons break down into quarks, the fundamental building blocks of matter. The universe becomes a cosmic soup of energy and fundamental particles. This early universe was governed by laws of physics that are still not fully understood. Although we can't directly observe the Big Bang, we can detect its faint afterglow. This afterglow, known as the cosmic microwave background radiation, or CMB, permeates all of space. Discovered in 1964, the CMB is a faint whisper of radio waves coming from every direction in the sky. It's a snapshot of the universe as it was just 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. The discovery of the CMB was a major triumph for the Big Bang Theory, providing strong evidence for a hot, dense early universe. One of the key pieces of evidence supporting the Big Bang is the observed expansion of the universe. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He observed that distant galaxies are moving away from us, and the farther away they are, the faster they are receding. Imagine dots on the surface of an expanding balloon. As the balloon inflates, each dot sees the other dots moving away from it. Similarly, from our perspective on Earth, we observe distant galaxies moving away from us as the universe expands. The expansion of the universe has profound implications for its fate. While the Big Bang Theory successfully describes the evolution of the universe from a very early stage, it doesn't tell us anything about the very beginning, the moment of the Big Bang itself. Our current understanding of physics breaks down at this point, known as a singularity. It's a point of infinite density and temperature, where space and time as we know them cease to exist. The singularity represents a major challenge for physicists. Some theories suggest that quantum gravity, a theory that unifies quantum mechanics and general relativity, might hold the key to understanding the singularity. The singularity remains one of the biggest mysteries in cosmology. The Big Bang Theory does a remarkable job of explaining the universe's evolution. But like any good theory, it leaves us with some lingering questions. One such question is, why is the universe so incredibly uniform? Look out in any direction, and the universe on a large scale looks remarkably similar. The cosmic microwave background radiation, for example, has almost the same temperature everywhere we look. This uniformity is puzzling. Proposed in the 1980s, inflation suggests that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. Cosmic inflation provides an elegant explanation for the uniformity we observe in the universe today. To get a sense of just how rapid cosmic inflation was, consider this. The universe is thought to have expanded by a factor of at least 10 to the power of 26, that's a 1 followed by 26 zeros, in just a tiny fraction of a second. It's an expansion so rapid and extreme that it boggles the mind. This period of inflation is thought to have been driven by a mysterious field called the inflaton field. Think of it like a cosmic fuel that caused space itself to expand at an incredible rate. As the inflaton field decayed, it released its energy, reheating the universe and setting the stage for the formation of matter. While we don't have direct observational proof of cosmic inflation, it makes predictions that can be tested by studying the cosmic microwave background radiation and the distribution of galaxies in the universe. One of the key triumphs of cosmic inflation is its ability to explain the remarkable smoothness of the universe on large scales. Imagine the early universe as a sea of tiny quantum fluctuations, like waves rippling across the surface of a pond. These fluctuations would have created slight differences in density and temperature in the early universe. Without inflation, these differences would have been amplified over time by gravity, leading to a highly clumpy and uneven universe, very different from the one we observe. Cosmic inflation, however, stretched these quantum fluctuations to enormous sizes. These faint fluctuations are still imprinted in the cosmic microwave background radiation as tiny temperature variations. Cosmic inflation is a theory that pushes the boundaries of our understanding of the universe. It takes us back to the very first moments of creation, a realm governed by the laws of quantum mechanics and general relativity. While we don't have direct proof of inflation, it has passed several observational tests. The cosmic microwave background radiation, for example, exhibits patterns of polarization that are consistent with the predictions of inflation. The seeds of this large-scale structure were sown during the inflationary epoch, and they have been amplified over billions of years by the force of gravity. The study of cosmic inflation offers a glimpse into the universe's earliest moments, a time when the very fabric of reality was being stretched and shaped. Imagine the early universe as a cosmic kitchen, a place of intense heat and pressure where the ingredients for matter itself were being combined for the first time. In the first few minutes after the Big Bang, the universe was a seething cauldron of energy and fundamental particles. As the universe expanded and cooled, this energy began to condense into matter, following Einstein's famous equation E=mc2. This equation tells us that energy and matter are interchangeable, like two sides of the same cosmic coin. As the universe cooled, energy transformed into particles, the building blocks of everything we see around us. In the first millionth of a second after the Big Bang, the universe was a hot, dense soup of quarks, leptons, and their antiparticles constantly colliding and annihilating each other. But as the universe expanded and cooled, a crucial transition occurred. The universe cooled to a point where quarks were no longer able to exist independently. The strong force which governs their interactions became strong enough to bind them together into groups of three. These bound states of quarks gave rise to protons and neutrons, the familiar particles found in the nucleus of every atom. It wasn't until the universe had cooled for about 380,000 years that electrons could finally be captured by atomic nuclei, forming the first atoms. The first atoms to form were primarily hydrogen and helium, the two lightest elements on the periodic table. These elements were created through a process called Big Bang nucleosynthesis, which occurred during the first few minutes after the Big Bang. During this period, the universe was hot and dense enough for nuclear fusion to occur. Protons and neutrons collided and fused together, forming the nuclei of helium atoms, along with trace amounts of lithium and beryllium. The abundance of hydrogen and helium in the universe today is a direct consequence of Big Bang nucleosynthesis. In fact, these two elements make up about 98% of the visible matter in the universe. Heavier elements like carbon, oxygen, and iron were not created in the Big Bang. These elements would have to wait for the formation of stars, where the intense heat and pressure of stellar cores provided the conditions for their creation through nuclear fusion. After recombination, the universe entered a period known as the Cosmic Dark Ages. With atoms now neutral, they no longer interacted strongly with light. The universe became transparent, but it was also dark, devoid of stars and galaxies. However, gravity was still at work, pulling matter together into denser and denser clumps. Over millions of years, these clumps grew large enough for gravity to ignite nuclear fusion in their cores, giving birth to the first stars. These first stars were massive and short-lived, ending their lives in spectacular supernova explosions. These explosions seeded the surrounding gas with heavier elements, enriching the universe with the ingredients for planets and ultimately, life itself. The formation of the first stars marked the end of the Cosmic Dark Ages and ushered in a new era of cosmic evolution. As stars clustered together to form galaxies, the universe began to resemble the one we observe today, a vast and ever-evolving tapestry of light and matter. The Big Bang Theory is the leading explanation for our universe's origin. It's backed by a wealth of evidence, from the expanding universe to the cosmic microwave background radiation. But scientists are always searching for even better explanations, pushing the boundaries of knowledge. This means considering alternative theories about the universe's beginning. Some theories propose that the Big Bang wasn't truly the beginning. Instead, it might have been a transition from a previous phase of the universe. Imagine a collapsing universe bouncing back, leading to a new cycle of expansion. This is the idea behind some cyclic universe models. Other theories delve into the strange world of quantum mechanics. Could our universe have originated from a quantum fluctuation, a random blip in the fabric of space-time? These ideas are still very speculative, but they demonstrate the creativity and ingenuity of cosmologists. While the Big Bang Theory is well supported, exploring alternative ideas is crucial. It helps us test the limits of our understanding and pushes us to seek new evidence and explanations. Before the Big Bang gained widespread acceptance, a rival theory held sway for a time, the steady-state hypothesis. This theory proposed that the universe has always existed, with no beginning and no end. It was an attractive idea, offering a sense of cosmic permanence. To account for the observed expansion of the universe, the steady-state hypothesis proposed that new matter was continuously being created throughout space. This new matter would form galaxies, maintaining the universe's overall appearance over time. However, the steady-state hypothesis faced challenges as new observations emerged. The discovery of the cosmic microwave background radiation dealt a significant blow to the theory. The CMB provided strong evidence for a hot, dense early universe, a key prediction of the Big Bang Theory. While the steady-state hypothesis is no longer considered a viable model, it played an important role in the history of cosmology. It spurred scientists to develop new tests and observations, ultimately leading to a deeper understanding of the universe's evolution. Imagine a universe that expands for eons, then contracts, only to be reborn in a fiery explosion. This is the captivating idea behind cyclic universe models, alternatives to the Big Bang that envision a never-ending cycle of cosmic death and rebirth. One such model is the ekpyrotic universe scenario, which suggests that our universe emerged from a collision between two three-dimensional universes, or branes, embedded in a higher dimensional space. This collision would trigger a Big Bang-like event, setting the stage for a new cycle of expansion. Another intriguing idea is the conformal cyclic cosmology model, which proposes that our universe undergoes an infinite number of cycles, with each cycle leaving an imprint on the next. These imprints could potentially be detected in the cosmic microwave background radiation. Cyclic universe models are still highly speculative, but they offer a fascinating glimpse into the realm of cosmological possibilities. They challenge us to think beyond our current understanding and consider the universe on grand, almost unimaginable scales. What if our universe is just one of many, like bubbles in a cosmic foam? This mind-boggling concept, known as the multiverse, arises from some theories in physics, suggesting that our universe is not alone. One possibility comes from inflationary cosmology. The rapid expansion of the universe during inflation could have created bubble universes, each with its own set of physical laws and constants. Imagine a vast cosmic landscape filled with these bubble universes, each with its own unique properties. Another intriguing idea stems from string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. String theory allows for the existence of extraspatial dimensions, potentially leading to a vast number of universes with different configurations. The multiverse concept is still highly speculative, with no direct observational evidence to support it. Nevertheless, it remains a tantalizing possibility, pushing the boundaries of our imagination and challenging our understanding of the universe's place in the grand scheme of things. We've journeyed to the edge of our understanding, peering back billions of years to the universe's fiery birth. From a hot, dense state, the universe expanded, cooled, and gave rise to galaxies, stars, and planets. The first stars ignited, flooding the universe with light. Yet our cosmic story is far from complete. The universe holds many mysteries, questions that puzzle and inspire scientists. Science is an ongoing process of discovery, with many secrets waiting to be revealed. One of the most profound mysteries in modern cosmology is the existence of dark matter and dark energy. These enigmatic entities make up the vast majority of the universe's mass and energy. Dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. We infer its presence through its gravitational effects on visible matter. Dark energy appears to be accelerating the universe's expansion. This discovery revolutionized our understanding of cosmology. The nature of dark matter and dark energy remains one of the biggest unsolved problems in physics. Before the Bang, the ultimate frontier. The Big Bang Theory describes the evolution of the universe, but what about the moment of the Big Bang itself? This is where our understanding of physics breaks down. The singularity is a mystery in our understanding. Our theories, like general relativity, cannot describe this extreme point. Some propose the universe didn't begin with a singularity. It might have emerged from a previous phase, a big bounce. The quest to understand the universe's origin is a journey without a final destination. Each discovery leads to new questions, pushing the boundaries of our knowledge and imagination. The universe is vast and mysterious, full of wonders yet to be revealed. New telescopes and instruments are being built, probing deeper into space and time than ever before. Scientists are analyzing data from the cosmic microwave background radiation, searching for clues about the universe's earliest moments. The Large Hadron Collider, the world's most powerful particle accelerator, smashes particles together at incredible speeds, recreating the conditions of the early universe on a tiny scale. The pursuit of knowledge about our cosmic origins is a testament to humanity's insatiable curiosity. We are driven by a desire to understand our place in the cosmos, to trace our lineage back to the very beginning. The journey to understand our universe's origin is an ongoing adventure, one that will continue to inspire and challenge us for generations to come. And as we delve deeper into the mysteries of the cosmos, we gain a greater appreciation for the wonder and beauty of the universe we call home. The quest to understand the universe's origin is a journey without a final destination. Each discovery leads to new questions, pushing the boundaries of our knowledge. The universe is vast and mysterious, full of wonders yet to be revealed. New telescopes and instruments are being built, probing deeper into space and time. Scientists analyze cosmic microwave background radiation, searching for clues about the universe's earliest moments. The Large Hadron Collider smashes particles together, recreating early universe conditions. The pursuit of knowledge about our cosmic origins is a testament to humanity's curiosity. We are driven by a desire to understand our place in the cosmos. The journey to understand our universe's origin is an ongoing adventure. From a fiery speck to a vast cosmic tapestry, the universe's story is one of incredible transformation. We've traced our cosmic lineage back billions of years, witnessing the birth of stars and the elements that make up everything around us. The atoms in our bodies were forged in stars, eventually forming our planet. The universe's story is our story. The quest to understand the universe's origin is a journey of self-discovery. By exploring the cosmos, we understand our place in the grand scheme of things. Think of the universe as an unfinished symphony, still being written. We marvel at its beauty and complexity. The universe's story evokes awe, wonder, and humility. Its music is written in mathematics, physics, and astronomy. By studying these, we decipher the universe's secrets. Our exploration is far from over. New telescopes are capturing faint light from the first stars and galaxies. Scientists probe dark matter, dark energy, and the universe's first moments. The universe will continue to surprise us. Every discovery leads to new questions, pushing our knowledge and imagination. Embrace the unknown, for it connects us with the universe's vastness and mystery.